Hi, my name is Tiago Sousa, and I'm a postdoc working at Technical University of Denmark. And my today's talk is about fairness different agent for peer-to-peer electricity markets using reinforcement learning application. And in this talk, I will present our case of applying reinforcement learning to a prosumer that is a market agent inside of a peer-to-peer market, and apply this reinforcement learning application for this prosumer and learn the policy for the decision making process of a prosumer. And I will start by with the motivation of this work, then move on to elaborate on the prosumer decision making process in peer-to-peer markets. Then I will explain the implementation of the reinforcement learning agent, and I will show some preliminary results with our first test case in this application, and then finalizing with some conclusions and next steps. So why we care about the peer-to-peer market? We see that the way that electricity market is today should move from a decentralized way of clearing the market to a more decentralized because of the introduction of prosumers. So from the picture you can see that a more centralized way, and the way that it is currently the market clearing is using a pool system, and we should move on from this system to a more decentralized, which can be used through a peer-to-peer system, where every agent inside of our market can communicate and negotiate the amount of trading energy that he wants, defining the amount of that wants to buy or sell in different time steps. And why it's a better setup? Because of the amount of prosumers that is expected in the future and energy communities, and these prosumers are, and you can see it as residential consumers that are adopting more and more renewables technologies like solar panels or electrical vehicles and home batteries, and they become actors that can both have the willingness to buy or sell energy in the market because they have the means to produce and consume electricity. And therefore, it's more a suitable market use a decentralized framework. And under this hood of peer-to-peer markets, you can solve, and the decision-making process of the prosumer can be formulated as an optimization problem, and we can solve it using consensus ADMM and solve it iteratively and find the optimal solution for the prosumer. And a way to visualize this decision process is we have a prosumer I, as you see it on the left on the slide. And the prosumer I can communicate and can negotiate with several other prosumers from J1 to Jn, and each one of them has their own energy quantity and price, and then through an optimization process we can determine what is the amount of energy, total energy that the prosumer wants, which is the sum of all these bilateral tradings that he is negotiating with other trading partners. And besides you formulate as an optimization problem, you could also try to solve the same and mimic the same decision-making process as a reinforcement learning application, because our prosumer I can be defined as an agent on this reinforcement learning framework, and each time that the agent interacts with the environment, experiments with the environment, could learn it the optimal policy, could learn it the optimal solution every time that they experiment, and over time we could derive this optimal policy. So we could also formulate the same decision-making process as this using this reinforcement learning framework, and our agent will be, in this case, our prosumer I, and the environment will be all the prosumers from J1 to Jn that the agent can trade with, and through learning, through experimentation, we can obtain the optimal policy for this agent. And the way that we have our decision-making process for our prosumer, in this case, we could see similarities of this process like the multi-armed bandit case, which I analyzed and saw similarities with this problem that I was solving. And the multi-arm bandit case is a problem where we have a reinforcement learning agent that can observe several slot machines from the environment, and through experimenting over time, the agent learns the optimal policy that retrieves the highest payoff of these slot machines. And so every step n, the agent takes an action, so selects a slot machine, and then observes what the environment returns. And the environment in this case can return 1 or 0. 1 means success of getting the payoff from the action, 0 as failure. And our optimal policy is derived to the maximization of the total reward over all these step n's that the agent is exploring the environment. And so we can, in fact, model the prosumer decision making process that I showed before as a multi-arm bandit case, where the goals of our agent is to learn, and the optimal policy will be what are the best trading partners for our agent. That not, in this case, doesn't return the highest payoff like the slot machines case, but returns the fastest conversion time of settling the energy that our agent wants. So our agent that represents prosumer I defines the energy target that he wants to get, and the optimal policy is the one that retrieves the fastest way of getting this energy target by experimenting and selecting all the prosumers that helps to get this target reach. And so the way that we model is that our action space is all the prosumers from J1 to Jn that our agent can experiment. And then we define 3 parameters for each one of these prosumers, which is the energy quantity that he offers, the price that indeed in our work we are neglecting, and a probability of success, that is a sigma. And this probability of success works like every time our agent takes an action, so selects a prosumer, there is a probability of the energy that he offers be accepted or not, because this same prosumer that was selected for our agent can be negotiating with other players inside of the peer-to-peer market. And since he's also negotiating with other agents, the offers that we select might be accepted or not, because other agents might pay more, or because of other preference might be accepted instead of our agent. And so our reward signal follows this probability of success. If we get a success, we get a reward of 1. If it is a failure, we get a reward of 0. And the optimal policy is the one that maximizes our reward signal. And the state of our environment is the sum of all the energy quantities that we have been collecting, that the agent has been collecting. And whenever our state is equal to the energy target that we have it here on our prosumer I, is when our episode stops, is when our simulation from between our agent and our environment stops. And besides all these parameters that we define, it's important also to look to something else, which is a cumulative probability that is updated every step n. So in every step n, we have our agent selecting a prosumer, and in this is an example that we use. So an action of one particular step is selecting prosumer J3. Then we have our reward signal, that is a binomial distribution. And then our probability of distribution is equal to the sigma, that is the probability of success of our prosumer J3. And then we get our reward signal if it is 0 or 1. And every time that we get our action and our reward, it's calculated the cumulative probability using this expression, that this probability is updated every step n, and the agent can use this probability as a way to define his policy strategy for the next time step. Because if our probability is getting high, it's getting close to 1, then it's more likely that the action that we are taking before should be proceed for the next step. And so we should try it more often the same action, because our probability of success is getting higher and high. While if we have a probability, a cumulative probability that has been decreasing over time. So it means that our action is not so good to be proceed for the next step. So this could be a way to guide our policy strategy over several steps. And this is the whole algorithm that we implement for this reinforcement learning case. And I will not go too much in detail. I will just highlight the main blocks of this algorithm. We define as a first is that we have several episodes to experiment in our environment, and in each episode we define an energy target that our agent wants to reach. And after each episode, in each episode that when we define this energy target, we initialize the steps that the agent will experiment in the environment. And then we have a while loop where this goes on whenever our energy target is different from our state. So whenever our state is equal to our energy target is when this cycle, this experimentation between the agent and the environment stops. So this goes on until we get our energy target, basically. And so it starts this loop by an agent taking an action, selecting one of the other prosumers, and then observes the reward signal of this same prosumer. And if the reward signal is 1, so we have an offer that was accepted. And so we collect the energy of this offer, of our prosumer, or the energy can be 0 when our reward, of course, is 0. And then our state and the total reward are updated, and the cumulative probability is also updated based on this action and reward signal. And then we go on to the next step until our while loop, as I said before, stops. It means that we got the energy target that we defined for this episode. And so we use this algorithm for using 3 different strategies for our action, and to see and to compare what are the policy strategies that can retrieve us the optimal policy that we want from this work. And so we use 3. We use the random policy, epsilon greedy policy, and a Thompson sampling policy. This last one, the Thompson, use the cumulative probability that has been updated every step as a guiding for our action to the next step. And so we use this algorithm and these policies for a case where we have our agent trading energy with 15 other prosumers, and we experiment this for 100 episodes. And on the right, you see the probability of success that was defined for each one of our prosumers. And the idea is that these policies, and see what are the policies that can identify, which one of these 3 policies, can identify the prosumers that give us a higher success. So, and the idea, and what we expect is that one of these policies will get that both prosumer 4 and 5 give us the highest success to be accepted. So they should be more often tested than others. And indeed, we can see that in the results. This is the results of 2 of our policies. On the left, you have the random policy. And in this case, as you see it, we test several prosumers, and therefore take us a lot of steps, especially in the beginning. There is no offer accepted. And then we also have several gaps of 0 energy. So it takes a lot of steps to get convergency. And on the right, you have already the Thompson sampling that follows this cumulative probability that we update. And this already makes that after the initial steps, the policy starts to insist more on the action of selecting prosumer 5 and selecting prosumer 4, and therefore starts to be accepted more often energy. So we are able to reach the energy target faster than using a random policy. And these were the initial results that we get it. And now I will go to the conclusions of our work so far. So these preliminary results indeed give us the idea that the agent is able to identify the best trading partners, and the policy that we retrieve from these experimentations is that the agent selects the prosumers that have a highest probability of success, and also highest reputation, which is derived through this cumulative probability that is updated every step. And as next steps that we want to proceed to investigate more the application of reinforcement learning is to compare the same framework that we test with a benchmark approach to compare and to derive how fast is and how good is this the optimal policy that we can derive, and also explore other reward signal functions because we use a reward signal function that depends on a probability of success that we define, but we could use other attributes like the price or even other attributes like the risk. And the last one is to investigate the scalability effect when we want to apply this same framework to bigger cases. We just applied as initial test case 15 prosumers, but we would like to see the effect when we apply to cases with many prosumers that wants to trade energy and see the effect of this scalability in our framework. And with that, I conclude my presentation, and I hope that you have enjoyed and as much as me, and I hope that you like the work, and looking forward for your questions in the Q&A session.